So, for our potential water system in St. Mark, we decided to go with a physical, biological, and chemical treatment process that would be operated with supervisory control and data acquisition systems. During this process, there will be extensive screening and shedding for initial influent. Any effluent collected would be drained into the Caribbean Sea. The levels of chlorine and other chemicals that may be present are not of toxic levels that would be detrimental to the hydro ecosystem in the Caribbean Sea. The facility would be placed on top of a mountain near St. Mark to conceal sewage odors, as well as being less likely to suffer from damages caused by reoccurring natural disasters such as hurricanes and floodings. This location was also chosen because Haiti is a very mountainous island, so there was not much of an alternative in this case. In terms of bar screening, after passing partial flume, which measures influent, the raw wastewater will pass through a series of mechanically cleaned bar screens. The first bar screen will be 1.5 inches for the opening space to allow larger objects like plastic or fabrics to be discarded. The second bar screen will have a much finer bar opening at 3/4 of an inch to filter out smaller objects. And finally, waste from screenings will be rerouted to a shredder and will then be dewatered before being delivered to a landfill.
Okay. Hey guys, so following the bar screens, the raw wastewater will flow through to a grit chamber, and this is kind of a cylinder that almost acts like a tornado, where the water comes in and it really kind of swirls around, and by doing so the grit is collected in the center of the chamber, which is how it is also discharged, is in the center of the container below, as you can see in figure 8, that grit discharge in the center. As the water is separated from the grit, it flows through to the outlet arrow, which you can see also in figure 8, and that's it for the grit chamber. Following the grit chamber, the water is flowed through to primary clarifiers, which we decided on a sedimentation process. And so in order to meet the 90 megaliters per day influent that our treatment facility will be seeing, we decided on 4 large sedimentation tanks. And here is a little bit of math, by the way, 2-hour detention time for each tank. So with that in mind, we decided to have a 3-hour capacity at all time for 4 tanks, as you can see below. And that will prevent the overflow with a 2-hour detention time. And so we figured it out at 2,812,000 liters, which is a lot. And that's each tank, 4 tanks. And as you can see here, the height of one tank is 10 meters. The diameter of the tank is 19 meters. And so these are some big tanks. And so here is a diagram of the primary clarifiers. And this is just giving a little bit more of a rundown. So as you can see here, the influent flows in from the grit chamber on the right. And so the influent flows into the cylinder, which is the primary clarifier. And it's going to settle out organic solids, BOD, and all of that stuff. And the settled sludge, as you can see, will come from the center down. There's almost like a drain. And that settled sludge will flow through down for dewatering. And on the left there, the water will next flow to biological towers. So, biological towers. Following the primary clarifiers, water will be pumped into 4 large biological towers for an activated sludge process. And so there's that lucky number 4 again, and we really settled on that. It's nice to always have additional units in case of maintenance. I mean, adjustments can always be made in order to meet the demand. And so that's why we decided on 4 tanks of clarifiers and biological towers, and to also meet the large demand, by the way. And the good thing about biological towers, it's really good about with concealing odors, effective treatment and removal of organic solids from filter medias in towers. And the way they work is the effluent trickles down through a combination of filter media, allowing biological processes to occur, such as BOD consumption, and which leaves behind a biofilm, which is again flowed through a separate almost drain and dewatered and formed into biosolids. And again, that's just repeating, flow through to a secondary clarifier for further sludge settling. So, after the biological towers, we're going to go to another sedimentation clarifier. And these are the exact same as the primary. Different tanks, but the same kind of setup. 4 tanks, 2,812,000 liter sedimentation tanks, which is the same. And again, 2 hours of detention time. And this is really going to remove the suspended solids and remaining BOD through settleability. The settled sludge is sorted through the bottom of the tank connection for dewatering and manipulation into the biosolid. Following the secondary clarifier, we can consider the water for the most part treated. It does, however, still need to be disinfected, and so that's where it'll flow next into basins called clear wells, and they are held there for disinfection by chlorination. We settled on chlorination because it's effective and it's affordable. Additional treatment and nutrient removal such as phosphorus and nitrogen may be required, and that of course depends on the influent quality, which will have to be determined at a later date. We don't quite know what we are dealing with there yet. So for the biosolids, which we've mentioned a few times, that's that it's coming out the bottom there, and that's your organic solids and your BOD. Following thickening and dewatering by gravity belt thickeners, the biosolids will be removed by a third party and spread around Haiti's agricultural lands. For the cost, our civil engineers are still currently working on a reliable estimate. This is a working project, and as such, it's difficult to give an extremely reliable estimate at this time. However, what we've done instead is looked up similar projects or estimates and use that against what we project our cost might be. And our project will likely be very different, by the way. I mean, it is in a third world country. Labor costs are probably far more affordable. There's probably a lot less barriers than building in say, the US. And so what the U.S. section of the International Boundary and Water Commission has stated, the estimated capital cost for construction of a 25 megagallon per day secondary facility in the United States in 2008 dollars is $101 million. And so for a comparison, our facility will be constructed for a capacity of 19.5 megagallons per day, which is considerably less than the plant mentioned above. And of course, the other factors, I mean, third world country, Haiti is probably going to be a lot more affordable than the US to build in. And so that kind of gives us a working idea of what we're looking at as far as a cost. Okay, that's it. Thanks so much, guys, for watching.